Okay, notes 2, sampling distributions of sample proportions. So we have a parameter is a number that describes an aspect of a population. N describes the total population size. P describes the total population proportion. Mu describes the total population mean. Statistic, which is a number that is computed from the sample data. N represents the sample size. P hat, the sample proportion. And X bar, the sample mean. When taking a sample and gathering the sample proportion, we know that it will not be exactly equal to the population proportion due to sampling variability. The idea is that there is natural variation to samples. So we're going to look at both of them here. So a population distribution versus a sample distribution. So for a population distribution, only one population distribution, okay? Meaning this is taken of one single population. For proportions, this is categorical data that is broken up into success and failure. So the population size here is going to be adding the successes and then adding the failures, which is going to give us 400. The proportion of success, P, is going to be the number of successes, which is 140, divided by the total population size, which is 400, and that gives us 0.35. For a sample distribution, that means we have many sample distributions. Each sample distribution contains a P hat value, which represents the proportion of success. So in the sample size, again, would be adding each of these bars together for failure and success, and we get 40. And then P hat, the proportion of successes, is going to be the number of successes, which is 18, out of the sample size, which is 40, and that gives us 0.45. Then we have a sampling distribution. There is only one sampling distribution, just like there is only one population distribution. The sampling distribution takes all possible P hat values from every possible sample distribution of the same size N and puts them together. This creates a unique sampling distribution with some common properties. So when you see sample distribution, I want you to think, okay, we did this one simulation in class together. So just our class. Okay, we did it one time. A sampling distribution is, let's say we had a bunch of classes who did the same exact simulation and had the same exact number of students in those classes. We would take all the data from all the classes and put it into a sampling distribution. So the mean of a sampling distribution for sample proportion is mu of P hat, and the standard deviation of a sampling distribution for sample proportion is sigma of P hat. All possible samples of size n equals 40 are found, and the P hat values are put together in a distribution. So think of each of these pieces of data here, all of these different pieces of data found and created this normal distribution, okay? So they give us the values for the mean and standard deviation, and that the mean was 0.35 and the standard deviation was 0.0754. And we're going to learn how they found those in just a moment. So properties of a sampling distribution. So first let's talk about the center. When we start taking samples of a population, we have to revisit an earlier question in the year, and how trustworthy is a statistic at being an estimate? Well, a sampling procedure is biased if it tends to systematically overrepresent or underrepresent certain segments of the population. To avoid bias samples, we make sure that our samples uses random selection, a statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the value of the parameter being estimated, or in other words, if mu of p hat is equal to p. In our example, mu of p hat is equal to 0.35, and our population proportion was also 0.35, which means we could use that statistic to estimate our parameter, and it would be an unbiased estimator since mu of p hat and p are both equal to 0.35. Okay, then we're talking about the shape of a sampling distribution. So it says no matter the shape of the population distribution, the shape of the sampling distribution will always be approximately normal, as long as a condition called the large counts condition is satisfied. And the large counts condition states that NP is greater than or equal to 10 and N times 1 minus P is greater than or equal to 10. So this means that the sample size times the probability of success is greater than or equal to 10, and the sample size times the probability of failure is greater than or equal to 10. As long as N is large enough, we can say that the distribution will be approximately normal. However, it will never just be normal. So if you are to describe the shape of a distribution and you say normal for these instances, you will get marked wrong because we are only approximating it. And the reason for this is the central limit theorem, which we will talk in another notes. Then we have spread. So it says statistics will vary from sample to sample due to sampling variability. However, larger samples have less variability than smaller samples. The spread of sampling distribution does not depend on the population size, but instead depends on the sample size. For independent samples, sampling without replacement, of a categorical variable from a population with the proportion p, the sample distribution has a standard deviation of sigma of p hat is equal to the square root of p times 1 minus p over n. So that's the square root of the proportion of success times the proportion of failure, all divided by the sample size. If you're sampling without replacement, the standard deviation of the sampling distribution will be slightly different. However, as long as we use a special rule, the difference doesn't matter. That rule is called the 10% condition. As long as this condition is satisfied, we can use the above formula to calculate the standard deviation of our sampling distribution. The 10% condition is n is less than or equal to 0.10 times n, or in other words, the sample size is less than 10% of the population size. If a problem does not mention population size, we have to describe n with words. So problem doesn't mention sample size, describe n with words. In our example above, we had sigma of p hat is equal to 0.0754, and they found that using that formula of the square root of p times 1 minus p over n is equal to the square root of 0.35 times 1 minus 0.35, all divided by 40, and that gave us the answer that they found there. It is important to note that you only need to check the 10% condition when you are sampling from a population. When we have an experiment, we're not sampling, therefore this condition does not need to be checked. So only need to check if we are sampling from a population. So let's look at some examples. So it says a recent study looked at the percent of young adult women who got less than 7 hours of sleep a night. In this study, we say that 45% of women get less than 7 hours of sleep at night. What is the probability that a random sample of 50 women will result in the same proportion of 50% or higher? So we're still following our 4 C's, and that first C is to communicate. So when we communicate here, we're always going to describe P. And P is equal to the proportion, and then the rest comes from the problem. So we're going to write it word for word, of women who get less than 7 hours of sleep a night. And then we're going to write down our probability. So we're trying to find the probability that P hat is greater than or equal to 0.5 because it wants us to find if the sample proportion of 50% or higher. Then for our second C, the create, this is where it's a little different. So we're not just setting up the probability and finding z-score and all that. Instead, we have to prove 3 things. The first thing we have to prove is if it's random. And this is the easiest to prove because we just have to look back at the problem and see if they use the word random. And if they do, we're just going to repeat what they said. Well, they said they did a random sample. And so that's how they got mu of P hat is equal to 0.45. Then we have to prove independence. In order to prove independence, we use the 10% condition. And remember, the 10% condition stated that the sample size has to be less than or equal to 10% of the population size. So we can say 50 is less than or equal to 10%. And since we're not given the population size, we're going to list what the population is in words. So we're going to say, well, N is equal to all young adults, women in the world. Right? So that's assuming to be a very, very, very large number. So 50 is definitely going to be less than 10% of that. So because of this, we're able to find sigma of P hats by using the formula. So 0.45 times 1 minus 0.45 all over 50. And this gives us 0.0704. And then lastly, we have to prove that it's approximately normal, and we do that by using the large counts condition. And remember, in the large counts condition, we have to prove that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So we have 50 times 0.45 is greater than or equal to 10. Well, that's good. Okay, because about 50% of 50 is 25, and 25 is greater than 10. And then 50 times 1 minus 0.45 is greater than or equal to 10, which is also good. So because of this, we can assume that it's approximately normal. For the third C, the calculate portion, that's where we write out our probability of what we're trying to find, and then we go straight to Desmos. So this is the probability that P hat is greater than or equal to 0.50, where P hat follows a normal distribution, and I'm going to move this so I have more space, of mu equal to 0.45 and standard deviation equal to 0.0704. And I'm going to go to Desmos. Where did Desmos go? Right here. Okay, and I'm going to switch out my normal distribution numbers here. Well, actually, this is a new video. Let me start from the very beginning. Remember, you go to add, inference, probability distribution. We type in our mean, which is 0.45. Type in our standard deviation of 0.0704. Hit create distribution. Click on the drop down, and we're finding greater than or equal to, so that's the right region. And I'm going to type in 0.5. And that is going to give me my answer here of 0.239. And then the very last part, so I'm going to get out of this real quick. The very last part here is going to be to the conclusion, so we need to write our sentence. So the probability that a randomly selected, the probability that a random sample of 50 women will result in a sample proportion of 50% or higher who get less than 7 hours of sleep is about 23.9%. Okay, let's look at another example. It says Dane fails to study for his statistics final. The final has 100 multiple choice questions, each with 5 choices. Assume all questions are independent and that Dane has given himself over to the gods of chance and randomly guesses on each of the 100 questions. So number 1 says, what is the parameter and context of the problem? Well, P, man, oh man. Okay, P is equal to the proportion of questions Dane gets correct. Number 2 says, what are the following values? Well, N is the number of questions, so 100, and P is the probability of success, which is 1 out of 5, because there's 5 answer choices and one of them will be correct, which is 20%. It says, is the sampling distribution approximately normal? Why or why not? So we have to use large counts. And so we need to prove that 100 times 0.20 is greater than or equal to 10. And 100 times 1 minus 0.20 is greater than or equal to 10, which is good. So we would say yes. It's approximately normal. Then it says, is the sampling distribution unbiased? Why or why not? We would say yes, since he guesses on each question. Make it more specific. Let's say he randomly guesses on each question. Number 5, do we have to check the 10% condition here? Why or why not? So we would say no, since each guess is independent. And remember, we use the 10% condition to prove independence, and since it already tells us that it's independent, we don't need to prove anything. Okay, then it says, what are the following values? So mu of p hat is 0.20, and sigma of p hat is equal to the square root of 0.20 times 1 minus 0.20 all over 100, which gives us 0.04. Then it says, what is the probability that Dane will get between a 25% and a 50% on the test? Show all your work for the calculation. Well, we're trying to find the probability that 0.25 is less than or equal to p hat, less than or equal to 0.50, where p hat follows a normal distribution of mu equal to 0.20 and sigma equal to 0.04. Okay, so I'm going to go ahead and go back to Desmos. I'm going to put in these new distribution numbers here. So 0.2, 0.04. Inner, because we're between two values, and it's going to be 0.25 and 0.5. And that gives us an answer of 0.106. And so we have to write our sentence, and that's the last step. And we would say that the probability that Dane gets between a 25% and 50% is about a 10.6% chance.